Andre, we need to unmute. You're still muted.
Okay, thank you everyone for joining this call, and going to present my multitasking operating system GeckOS. And luckily we've had, I hope Sebastian will link that in the description, the multitasking on the Commodore 128 call before that, so I can skip over a little bit of some of the details. So why is multitasking a challenge? We've heard about that. We have fixed addresses for the stack and zero page. We have no position-independent code, and we have no memory protection. So looking at the past, when I started all that, it all started in 1990 or maybe 1989 when I built my initial Commodore PET clone, and it was using an MMU. So here you can see a picture of that machine. So the MMU was able to split the 64K of memory into pages of 4K each, and could map that from a maximum of 1 megabyte of memory that was available on the bus. So because the BIOS board, what I call it, had 32K of RAM, and the video board has 64K of RAM. I already had 96K in the default configuration. So that was very nice, and it ran up to 2 megahertz. So that was what was GeckOS was made for. So the MMU was translating the upper addresses, the video card with the CRTC like the PETs, mostly PET compatible I/O and other I/O on PCB cards. So when you talk about multitasking, so I shortened this all a bit because we had this talk before. We need to look at where each task resides in memory. And the memory management unit on this PET clone made it very simple, because every task had its own memory map. So we have the kernel that has some 4K of kernel memory, private kernel memory in the bottom, where it has its own stack and own zero page. And we have the kernel itself, which is 4K in size on the topmost page. And that was what the kernel would see. And it could, of course, because it's a kernel, it can also remap other pages of memory to access memory that's actually owned by one of the tasks. And each task has its own, has the same kernel mapped into its memory, but it has its own separate memory RAM at the bottom of the page. So it has its own zero page and stack. So that was easy. You could just reserve some of the memory in the 32K here static RAM or in the video card RAM to map that to the different processes. So it is even better than the 128, who can that can remap zero page or stack. But I could also completely remap the whole 4K, and there were programs that just ran in this 4K very fine, much fine, and all the rest of the memory was just not writable. So how did GeckOS work, or GeckOS 1.0? And it's basically still valid in GeckOS 2 point something. It's a microkernel, and the kernel is only doing the inter-process communication. So we have the devices part of the kernel, we have an environment part, that's what I call it. It's the management of the memory areas of the, if you go back to the previous page, each task here had its own, what I call memory environment. And that's going to be more featureful in version 2, but I come to that later. And there is a file system manager, which is basically mapping drive numbers to file system tasks. So you could send as a normal shell or monitor or whatever task, you can send a message to a file system manager to say, okay, let me load or open this file from drive 0, 1, 2, 3, or 8, A, B, C, D, and so on. and the file system manager would map it to different running tasks in that that are running in parallel, all on the same system, and then the file system, the task specific for that device drive number would react. So, for example, I have a device file system that maps devices to files, because I was kind of looking at the Unix philosophy, everything is a file. I have IEC bus, which is able to support, actually it was able to support parallel IEEE 488 from the pad before it was able to support IEC from the Commodore 64. I have, here it's still called FS-IBM. I should change that to FS-FAT. So you can use PC floppy disk drives, which I have an expansion board for my pad clone. Those are the main file systems supported right now. And there is the stream module, which does the data communication between tasks, which is unfortunately still byte oriented, but there are some plans for maybe call it GeckOS next generation. And then there is a memory management that manages all the memory allocations and so on. And devices are here on the other side of the kernel, and they are running in the interrupt. So they are being called from an interrupt, which is typically running from the screen interrupt, so every 60 hertz or so on. So that was GeckOS 1. What further development, and that was in 1990 or something. So I created a TCP/IP stack using SLIP, serial line internet protocol. I actually had a GeckOS machine, Commodore 64, with the user port 9600 baud interface on the internet, serving one page and one little GIF from a 1541, which is hellishly slow, but it worked. Occasionally it crashed, but still worked in some way. You could actually you can log into the operating system from the internet. Not on this version, but if you put it on some local network. And then going to version 2.0, I did a kernel rewrite. I implemented threading, and that means I have a complete hierarchy. I have the memory environment that can have multiple processes or tasks, and each task or process can have multiple threads. And this is all stacked, and every stack has its own thread. I have dynamic memory management. I have relocatable binaries, because in the original MMU version, I could just assemble the programs to a fixed address, because that's where the program started in their own memory environment provided by the MMU. For the C64, I needed a way around that. My way around that was to create the 065 file format together with and then build it into the XA65 cross assembler. So I was able to build my binaries as cross architecture binary that run on all the supported platforms on that OS. It's even using late linking because the kernel on the different architecture is on different addresses. The libraries are on different addresses, but you can just load the programs file. They will be relocated to their address in memory when loaded, and it will all linked to the current address of the kernel and the library. So what other features are there that have been in 1.0 already? Some have priorities. You can decide how many time slices a task can get. You have virtual consoles. We've seen that in OS 128 as well. Signals, semaphores, backgrounding, redirecting, piping. You can use shells, very similar to a Unix shell. There is a standard library I call lib6502. I think there is another. I think Lunix. I'm not sure. Is using, or some other operating system has support for those as well. and already mentioned the cross-assembler and the file format. Currently supports, of course, my my clone, which the latest edition, if you can see in the camera, is still here. The Commodore 64, even the 32K pad, but this is basically so memory constrained that you can only run, say it's tech demo. But the 8296 Commodore pad, which has 120K of RAM, where you can actually use 96K of RAM in a special banking configuration, is very nice. Unfortunately, the 128 is still missing due to time constraints, but the plan is actually to do that as well and use the relocatable zero page and stack there for task switching. Demo time. So you just load it like that, and when it's loaded, can you see the widescreen?
Yes.
Very good. So let me get out of pause mode. So this is how it comes up when it starts. What you can see here is there is an init process that reads a list from what is still called some kind of ROM, yeah, and starts the processes in that boot image. You can call it init ROM disk, but it's not really something like that. But it's a boot image that has the init process, the device file system, and the IEC file system in here. And then it takes loads the shell from disk. So if you can look at the devices we currently have, and here's a difference between the previous one. It's also memory constrained. LS is an external program. LS is loaded from disk before it actually executes and shows the data from the disk. There you can see we have a serial device, which is the 9600 baud user port. So yeah, I can do NMIs. It's complicated, but it works. I have multiple consoles. I can do a shift tab, go to another console, 3 actually, even though there's 4. There's some null depth. You can pipe stuff in there, and it's gone. So if you go show uname, this is actually built in, so it's very fast. So it shows what the version of that one is. It's actually wrong because it should be 2.1. I have to change that. You can have, you can actually, because I said this is, all processes are in the same memory. They're not swapped out or anything. So I can have a program that shows you the memory allocation of that system. And as I said, it's relocating all the binaries every time when it's loaded. So you can see here, this is LSMem, is a special program that does that, and -z shows the zero page. And for every byte you can see, yes, every byte, you can see which process is actually using it. 0 is process number 27, it's the actual shell. 1 is process 34, which is the LSMem itself. What you don't see are those that are started from the boot image, which are hidden behind those others. Those are not used. So I can actually start another process on a second, terminal, second console. So let me show. Let me load that, and I'm going to cheat a little because time I'm going into warp mode, and you know I'm not into fast loader, and the reason for that is because I'm coming from the pad. The pad has a parallel bus. The parallel bus is about 5 to 8 times faster than IEC, so I never needed a fast loader. The first thing I did with my Commodore 64 was actually I gave it an IEEE 488 interface and converted my 1541 into parallel 2031. So if I have a call for action, for help, that's one of the things I could need some help. So what you have here is you have, I started on terminal, on console video 2, another shell. And if I switch over to the other shell, I have a second shell here. And this one is running, again, ls is loading from disk before it's actually showing the directory. So what? And there I'm back. I'm still on the other console. It's still there, and there's the other one running. And it works similar as has been shown, explained in the previous call. There is a buffer for each program. It writes its output to. This output gets sent to the console. The console is running in the background. So if I can start. I have a monitor, but it takes a long time to load, so I'm not showing it here. And let it run through all the memory and scroll it through. It will scroll in the background, and you can go to another console and do something else, and it will scroll by and continue to scroll. And the program will run as long as the console is taking the output out of the buffer. So now when I go to and show me the memory output of the system right now, you can see that there is, and this is now M is the, I'm going to, there it is, okay. And M is the memory map, so it's approximately by memory block. You can see the 0 is again the first shell, 1 is the LSMEM. And you can actually see there's two entries for the program, and one of those is the data that is used by the library, and 2 is the, and then the other one is the rest of the program. And there's a second shell that is running in the background. Yes, the other console. You can also do a PS, which is also loaded, and that's why I asked, because the other in the previous call it was very snappy. It has to be loaded from disk, it takes a bit until it starts. And then you can see here the init process, the device file system, the IEC file system, the shell, the PS command, and the other shell that I started on a separate console. You can see here this is the signal address, and it's all the same. The Commodore 64 only has one memory map, and it's not copied over. And the reason why this works is because the library that handles the signals is re-entrant, and that's what is this why it needs its own separate memory area. And you can send. And I'm going to show a demo program for a semaphore log. You can, which is from Tende, Glenn Holmer, he wrote, and it starts one process and logs a semaphore, and then runs another process that waits for that semaphore, and then you have to hit the key here to free the semaphore to make the program run. And if you go and look at the PS in the background, you can see all the events are running in memory. So you see the log and you see the block, and you could also see them. If you want to do that, you could see the memory map and so on. Then I press the key here. It should be. Okay. So the program has released the log. The second program has taken the log, the semaphore, and then released it again and ended it. So you have these different means of inter-process communication. Okay, so let me go through back to the slides. Keep time. I think I only have 2 minutes left. Okay. So if you want to program with GeckOS, that's very easy. You can use low-level kernel calls. You can use lib6502 level. It's all cross-architecture. The binaries are compatible, as I explained, using the relocatable file format. There's extensive documentation available in ASCII doc format about the different ports, about the kernel calls, about the library calls. For example, here is an example for the psem semaphore, which is actually in this demo, which I showed. So in the future plans, I want to expand on the controlling terminal, so you can actually do some kind of control C in a more standard way. I want to unify the communication between the different tasks, which is now byte oriented. I want to make it more block oriented to save more space. Much more, and I want to support the UltraPad, the Commodore 128, maybe even the Apple II, or the BBC Basic to it. And it's all open source. You can have it here. There's a video series I have on YouTube. There's also Sender's commentary on GeckOS. We even had put out some HTML documentation, which I can gladly link here from here. So that's it for a very short run through GeckOS. Thank you, and waiting for questions.
Many thanks, André. Maybe I will kick off the first question. You didn't mention any RAM expansion unit here. Is it? Did you try? Is it working? I mean, is it foreseen to be using that? And if so, would it be then possible to maybe, or if not, maybe if I was just thinking, would it be possible if you are using a disk or something, or some external storage, to use that as extra virtual memory?
There's two questions here.
Yeah.
The RAM expansion unit, I actually only got one this year or last year or so, because the Commodore 64 is not my primary development machine. I'm very much pet guy, and I'm working on these pet clones. But yeah, I have an idea how to hook the RAM expansion unit into a file system tasks, so that can actually be run as some kind of cache. So if you load a program from disk for the first time, it would be also stored in the RAM expansion unit, and then automatically taken from there. You load it next time, which would definitely greatly speed up the loading.
Mm-hmm.
The second one was virtual memory and paging. That's a good question. The problem is, if you page something out and you want to page it back in, you have to page it into exactly the same addresses.
Yeah.
And if you have such a memory constrained system like the Commodore 64, it's very difficult to. In the meantime, you have started some other processes and so on. To have that RAM, these address ranges actually available again. So in the 128 operating system we saw before, that was easy because there were actually only two. I understand, one process for the GUI, and the other one was basically swapping them out the background processes. And they were not relocated, so they all on the same on a static address. So that was working fine. I could do that similarly, but I'm not sure if I want to do that. That would be quite some change. So for now, I'm more concentrating on looking at machines that have enough RAM, and then see how that works out. Okay, has to fit into
Okay.
memory.
Maybe in version 3.0 then.
Yeah, maybe.
Good. Many thanks. Is there any other question? Yeah, really running late.
Yes. Just wondering, how do you exactly handle a stack per thread? Are you copying the stack around, or do you split the stack in multiple parts? Or
Actually, there's two options. Exactly those. Because it's a microkernel, you can have it in the full-fledged version like I've shown, or you can just use the 4K kernel, use the process switching and inter-process command, and build a minimum system. So in non-MMU systems, you have two options. You can split the stack, but that restricts the number of processes even more.
Yeah.
In this version, it's actually copying the stack over. But of course, it only copies from the stack pointer to FF. So, and what I found is this is not really much usually. There is not so much stack usage. I mean, if you're running basic Commodore Basic, which works on my full MMU machine, but not on the Commodore 64, because there's really not enough memory for that again. And especially not, or maybe it would. I have to try. But
yeah, if you
anyway.
just use the stack pointer, it's not that much copying. I can see
Sorry?
that. I said if you just use the stack pointer up to whatever the top of the process stack is, or the thread stack, then it's not that much copying. That's true. That should be workable. Yeah, you made an interesting comment about relocatable code, and I ran into exactly the same thing. Like, if I do that, then I have to move things around all the time to ensure that the space is available again. That's why I made a different choice. One comment: it's not like one process running the user interface. You could. There are really two user processes in memory at the same time, and there can be 32 of them if you want to. That's just a lot of swapping. The kernel is its own space, and it doesn't need the normal space that is used by processors. So the consoles and all that it doesn't need any RAM from that's normally used for a process. So you can have two real complete user processes, which are multi-threaded and can use a user interface on one thread and whatever in the background on another one. But that's quite similar. I was surprised by the similarities, by the way, by looking at what you're doing and looking at what I'm doing, and seeing also the different choices we made due to different hardware considerations, memory considerations, and so on.
I see. There is also C64 OS. Greg, I think, I don't remember the exact name. So he's doing also like stuff with the REU and all that. So I thought, well, I should probably support it. I only have limited time available, and as I said, my main development platform are my pet clones. So I'm not very experienced with the REU and fast loaders and that stuff. So if anyone feels inclined to help me, that would be very.
I have commented source code for a GVDOS implementation if you want. That is open source. It's GPL though, so you need to be open source as well. That's the only thing.
Yeah, of course I'm on GPL. So
well,
GeckOS
then that would work.
Yeah.
Good. But let us maybe park just looking at the time, Bart and Anders. Many times. I think it's really interesting, but you can also maybe park that discussion and take it offline. I think just for the sake of the of the time. But I understand it's of course overlapping or very close in terms of the approach. The two systems and very, very interesting. Many thanks, Andre.
Thank you, everyone.
And thanks as well to Dusty for having allowed the switching or the swapping on the agenda. I will stop the recording now.